So in this video, we're going to take a look at text encoding. How do we represent text characters in computers? We saw in the last couple of videos how we represent quantities, right? And, I like this sentence I wrote here when I was kind of like doing the outline, adding to the outline of what each video covers. But computers store binary numbers easily because they have switches that are either on or off. I thought, when I wrote that, I thought, wow, that kind of explains it well. So maybe you want to pause this video and just read that for a second and kind of reflect on that. But that's how binary works really well with computers. So in this video, we're going to look at hexadecimal and octal. There's a couple of things I realized I should probably say about those two things to you. We haven't even said anything about octal, so I thought I'd mention that. And then we're going to look at ASCII and UTF-8. So first order of business, hexadecimal. It's often called hex. So when you hear people talking about hex, that's what it's called. And sometimes it has a 0x prefix indicating it's hex. And the reason it has that 0x prefix, the prefix 0x is widespread due to its use in Unix and C and related operating systems and languages. So if you ever see 0x in front of a bunch of characters and that are numbers 0 through 9 or the letters A, B, C, D, E, F, right? Then that's hexadecimal when you see that 0x prefix. I'll show you what that video is about in a second. And then there's also another, so we looked at decimal, we looked at binary, we looked at hexadecimal. There's another numeral system, octal. And octal is just base 8. It's base 8. And so octal is often called oct. And my question for you is, how would you represent the number 42 in oct? Right? So maybe you want to pause the video and see if you can pencil that out. But it's base 8, so you're going to do base 8 to the 0, base 8 to the 1, 8 to the 2, 8 to the 3, and get all your places, and then figure out how do you write the number 42, or the quantity 42 in oct. And then my next question for you to think about for a second is why? Why oct, right? Why base 8? And here's the answer. So if you want, you can pause the video and think about that for a second, which I encourage you to do because that kind of reflection keeps you engaged and makes your mind work. And that's actually how you learn things. At least it's helpful from what I've seen in all my years of teaching. So base 8 oct. The reason we have oct is because we work a lot with bytes. And bytes are 8 zeros and 1s. And so it's sometimes really helpful to have base 8. So in this video, we're going to see also ASCII and UTF-8. So let's go take a look at ASCII and UTF-8. And the first place I want to start is with Wikipedia. And so here's Wikipedia, and they talk about ASCII. And ASCII stands for American Standard Code for Information Interchange. This is like a total, almost a paradox, right? What do they call that phrase where it's like two things which are incongruent, like American and interchange, right? You think it wouldn't be just limited to America if we wanted to interchange information. But so, back in the day, the world wasn't quite so globalized, and now we're just a very, much more interconnected around the planet. And so the ASCII, American Standard Code for Information Interchange, that's what ASCII stands for, was a coding scheme for English. And back in the day, they had coding schemes, like every language had its own coding scheme. And so, this is what it looked like for English, right? Like we come down here and we say, hey, the letter capital A is the number in decimal 65. And the way we store that using a single byte of memory, 8 zeros and 1s, so 8 switches, circuits or switches that are in some configuration of on or off, the way we store that, in switches, porch lights, if you want to think about it that way, is like that, right? Because that is the number 65 in binary. And so there would actually be, and you'll notice here that there's only 7. So the 8th place is used for something else. And so 7 will take us up to, if we have 7 characters, right, 7 zeros and 1s, how many things can we store? We can store 2 to the power of 7. So 2, right, 2 to the power of n, that thing we learned, 2 to the power of 7 is 128. So we could store 128 characters. And for English, great. What else do you need, right? Because 128, we got 26 letters of the alphabet. right? How many letters in the alphabet? Whatever. And well, we've got 65 to 90, and that would be 25 in each one. So that's 26, I'm pretty sure. That's funny. I got to check that out. Characters in alphabet. 26 letters. Okay. I don't know why I was having doubt on that. So, yeah, the letter A, that's how we'd represent it in the computer. And lowercase a, it would be represented like this. And something that's really, and so, you know, if we had the plus sign, it's the decimal number 43, and it's represented like that. And something that's cool about the way they made ASCII is you'll notice that the first letter in capital is the first one here, and then the first one there, right? And so, you know, and then this is like, you know, B, and this is C, and this is D, right? So if you just sort of like, you know, don't look at these three right here and just look at this side, you know, you can see the letters, you know, kind of increasing. But anyhow, right, the thing that's cool is one there is that's the uppercase, and then here's the exact same thing except with one more one right there, and that is lowercase. So you can just sort of see that congruence there, and how they align those for that to work. Anyhow, so that's ASCII, and the Japanese, Chinese, you know, there's all these other coding schemes out there, and Japan even had like several different coding schemes in their own country, and it was really kind of a big mess. And if you wanted to share code from one computer in Japan to another computer in Japan, they might not even interpret characters correctly, because when they go to look up, okay, this series of on and off represents what, right? If you had a different coding scheme, it'd be looking up something else. And if you wanted to exchange information from Japan to America, you know, forget it. And with only 127 characters, we can't represent all of the letters in the world. So they created a new coding scheme. That new coding scheme is UTF-8. And UTF-8 is based upon the Unicode coding scheme. And UTF-8 is the world's most popular coding scheme, right? So here it is. You know, popularity, whoop. ASCII, whoop. You know, because we needed to be able to, you know, share information around the world, obviously. And it uses 1 to 4 bytes, 1 to 4 bytes for UTF-8. So we're storing up to 32 characters, 4 times 8, right? 4 bytes, and each byte is 8 bits. We're storing up to 32 zeros and ones, 32 binary digits for each character in UTF-8. And the way that works is the first bunch of characters in UTF-8 are ASCII, right? So all of this stuff in ASCII, same thing in UTF-8. So number 69 in UTF-8 represents the letter capital E. And so that's the same in UTF-8. There's a great video which talks about UTF-8, 10 minutes long, character symbols in the Unicode Miracle computer file. So I really encourage you to go check this video out, because it'll kind of give you a little bit more background into UTF-8 and all these different coding schemes. So that's ASCII, and that's UTF-8, and that's Unicode. And Unicode, I'll just read this because I thought this was good, is computing industry standard for the consistent encoding, representation, and handling of text expressed in most of the world's writing systems, right? So it captures pretty much, you know, all the characters and all the languages all over the world. And so that's ASCII, that's UTF-8, that's this great video. And in the next video, we are going to see how to write some programs and some Go code, which will, you know, show numbers in decimal and binary and hex. And then you'll learn a little bit about format printing and format verbs and escape characters, and you'll see the syntax for a loop. And then we're going to create a program that prints the first 200 characters of UTF-8. So we're getting into some cool programming stuff, and then the next sections is going to be all Go programming. So we're just laying the fundamentals here, but these fundamentals, this foundation is important to understanding Go, because Go, you know, suffers no fools. You have to know this stuff. All right, see you in the next one.